Welcome to Microsoft Build, final session of the day. So hopefully I won't keep you here for too long and try to make it exciting. We'll have lots of questions. If it's too complicated, try to hold your question. We'll try to take it at the end. We'll have plenty of time for questions. So my name is Hari Pulapaka, and I am here. I'm the program manager for Windows kernel. And so my team runs a lot of the Windows on ARM project. Along with me, I also have Arun Kishan, who runs the software engineering team. And he will talk a little bit about how the x86 emulation layer works. So before we start, let me do a quick show of hands. How many of you have visited our booth on the convention floor, played with these devices, or even bought them? Woo, not too bad, not too bad. So that's good. So let's start. So the always connected PC, it's a new category of PC. It's a new device category that we are starting. It provides you the simplicity and the mobility of a phone, a mobile experience, and the creativity and the power of a PC, right? So that's what we're trying to birth a new category here. And if you think about this PC, it has 4 key categories, right? 4 key attributes. It has it's always connected. It has inbuilt LTE, right? Every model of this device will have LTE in it. And then the OS seamlessly switches between Wi-Fi or LTE. You don't have to worry about it. If you have a SIM and it's active, the OS will decide whether the Wi-Fi is there or LTE. The second thing, and this is key, like at least for me personally, is great battery life. The battery life on this device gives you days of usage, not hours, days of usage. And for me personally, this has been the most behavioral changing thing. I don't even carry my power card most of the time. In fact, this is the first time today I carried a power card for my demo device because it was like, it's a pretty big demo. I didn't want to try to push the demo guards on this point. The third thing, and this is key for me personally, this is just Windows. It's just Windows. It's the same Windows that you use on your PC, the same Windows that you use on your Surface laptop. It has the same features. It has Hello, Cortana, Edge, Pen, inking. Everything that you use is the same. It's not a different SKU. It's just Windows. And finally, after battery life, I think this is the other feature that, for me personally, again, has been the biggest home run. Instant on. It's just like a phone. You open the device, Hello kicks in, you log in, and it's ready immediately. There is no resume from sleep. There is no spinning circles, nothing. You just turn on the button, and it's in, right? So that is pretty huge for me personally. So why ARM? Right? Why add complexity to the developer's life? Why ask them to support one more architecture? You already have x86, you already have x64. So if you think about it, there are around probably hundreds of millions, if not billions of devices running ARM today. You have IoT devices, you have phones, you have embedded industrial controllers. If you look at devices from companies like Apple or Samsung, right, the performance per watt of the ARM processor is pretty sweet, right? It's ideal. You can get good experience. You can get great battery life. So the question really should not be like, why ARM? The question instead should be, why not ARM for PC? Right? It seems like we're there. So let me talk a little bit about the technical details of how we made Windows work better on the Qualcomm Snapdragon processor. So I don't know if you know, but ARM has this concept of a big little architecture. And when you think about big little architecture, it's really just 2 processors. They're the same processor, but they're clocked differently. What that means is the big processor, it's running faster. It has a higher frequency. And the little core is the same core, but it's running at a lower frequency, so that means it runs slower. The advantage of it running slower is that it takes less battery power. So the big core, it runs faster, takes more power. The little core runs slower, takes less power. And both of these cores, they're interconnected, right? So it's cheap, instantaneous for threads to move and migrate between the big core and the little core, right? It's easy. In fact, most users don't even realize this is happening. And so to take advantage of this architecture, what we did inside Windows is we added a new policy into the kernel scheduling, into the scheduling policy. We call this the heterogeneous kernel scheduler. What this does is it takes into account the user's activity, right? So if the user is using the device, all of the threads that the user is using, like all of the applications that the user is using, those threads, they run on the big core. all of the threads of the processes that are not relevant to the user, right? Your services or something in the background, they are kicked out, migrated to run on the little core. So this gives you a perfect and ideal example of how this device can get you good battery life, but also get good experience, user experience. So for example, if you're launching Outlook, so every thread inside Outlook will run on the big core, but your services, your indexer, your background tasks, all these ancillary threads, they run on the little core, and that way they don't consume a lot of power, but the things that you care about, they're snappy, instantaneous. And then the second key thing about ARM is the processor package size. So if you think about this, it's basically the Qualcomm Snapdragon processor is a SoC. SoC means system on a chip. What that means is all of the devices are part of the processor itself. There are no interconnects, right? So the GPU on the processor, the GPS, the sensors, they're all part of the processor and on the package itself, on the die, as they call it. And so this gives you innate, like, some extra power efficiency because just the bits don't have to move a lot of distance. There are no interconnects, there are no wires, right? It's just part and parcel of the processor. The other key thing that this gives you is because it's a mobile processor, it's smaller in size, right? And so when it's smaller in size, it leaves you more room in the PC to put a bigger battery. So if you think about it, you have a small package and a bigger battery. So that gives you a better battery life. That's another advantage. Again, the SoC, the Qualcomm Snapdragon processor, already includes the LTE. It's part of the processor. You don't have a USB that you connect on the side, right? It's part of the processor. So again, that gives you innate power efficiency. The processor is really smart about how to power it up, power it down, how to connect. And then finally, again, it's a mobile processor, so it gives you instant on, right? Touch of a button, it's on, everything responsive. So these are the first wave of devices that are going to support Windows 10 on ARM, right? So you have the Asus Nova Go, which is more of a traditional laptop form factor, right? It has full HDMI, USB ports. And then you have HP Envy and the Lenovo, which is more of a two-in-one. These are lightweight, thin, tablet-style devices. Now, when you look at these devices, the key thing to keep in mind is these devices are targeted at a mobile, lightweight PC experience, right? These are not your dev box. If you want a device for a consumptive experience, if you want a device to watch Netflix, to do browsing, to do Outlook, to do PowerPoint with great battery life and always connected LTE connectivity, then these are the devices for you. If you want to buy a device to do Visual Studio, Photoshop, right? This is not a device for you. So you got to keep that in mind. You got to keep the audience in mind. You got to keep the target device in mind. So before I go here, so what we did is when we first added Windows 10 on ARM support in around December, we reached out to a bunch of influential MVPs and asked them to use these devices as their primary device, and then give us feedback on the developer experience because we wanted to understand if there are any warts, if there are bugs in those devices. And so I don't know if you all know what MVPs are. MVPs stand for Microsoft Valued Professionals. These are, you can think of themselves as community volunteers, right? So they go out there on the internet, they help developers with their questions, they answer questions on the forums, they have pretty popular apps of their own in the store, and in general, you can think of themselves as Microsoft experts that are not part of Microsoft. They're not our employees. They are free community volunteers. And so we seeded a bunch of these devices with around 10 of them. And so I wanted to just show you quickly verbatim quotes from them that tells you about their experience. So here's Jeannie. Jeannie is actually the build MC. I don't know if you know that. She's one of the MVPs who's emceeing the build. So this is her experience. I traveled from Thursday to Sunday last week with my device. I used email, Skype, and a bunch of other things. But what I didn't do is I didn't charge the device, right? Thursday to Sunday, using it like a normal PC, no charge. This is Oren. He's talking about his battery life again. He's comparing his experiences with Surface RT or Windows RT that released many years ago and the iPad, how it never had power. And the new devices, Windows 10 on ARM devices, always have power. This is used. Here, what he's showing you, he's connected a bunch of devices to his HP Envy, and all of them worked. Now, the thing to keep in mind is these devices have a USB. They have USB-C or full USB. So all the peripherals that you connect to these devices, they are running with the support of the Inbox class driver. You don't have to install any driver, right? So if you connect a keyboard, it just uses the Inbox class driver. You connect a mouse, it just uses an inbox slash driver. This clicker, I didn't need to install a driver. It just worked. If you look closely, he actually has an Xbox connected. And he connected the Xbox controller using the Bluetooth. Again, the inbox class driver. So you get a lot of peripheral device compatibility without even thinking about it. You don't need to write drivers. Windows already supports all of these devices using the inbox class driver. So how did we do this, right? So what we did is we took all of the Windows source code inside that we have, everything that we have inside Windows, inbox components, and we recompiled it to ARM64. So this is ARM v8 instruction set for those really curious. I don't know if anybody cares, but that's the instruction set that we target. And if you think about it, Windows is cross-platform by design, right? Windows in its long history, we've supported DEC Alpha, DEC MIPS, PowerPC, Itanium. Windows has a history of supporting multiple architectures. So the code itself, our OS, is engineered, is structured in a way so that it's easy for us to move across architectures. I'm not saying it's easy in the sense there is no work, but our engineering system is designed to support and be platform independent. So if you think about Windows, or any operating system for the matter, right? Like it consists of two parts. You have the kernel, and then you have the user mode. The kernel is where your drivers, your hardware interaction happens, and the user mode is all of your experience, right? And so in this case, the kernel contains all of your GPU, your disk, your networking, your CPU. So all of these heavyweight hardware, these are all running natively. These are drivers authored either by Qualcomm or by Microsoft, and they are running natively as ARM64. And then in the user mode, you have your things like Edge, you have your Cortana, you have your services, and all of them are also recompiled and running as ARM64. And this is one of the key reasons why when you use these devices, they're snappy, they have good experience, they have good user experience, right? Because all of the Windows code, all of the inbox experience is all running natively as ARM64. So let me show you this. Let me show you a quick demo so that we can show what's real. And just to prove a point, I am actually demoing from my Asus Novago device right here. I did not use the build machine. I wanted to make a point here that this device is powerful enough for us to use full-on PowerPoint and use it as a real machine. And so as you can see, this is the Asus Novago. Like I said, let's show you the system properties just to avoid any doubts here. So there you have it. Right, so this is the Asus computer. It's 4 GB it's 4 GB RAM, 64-bit operating system. It's an ARM. It's a Windows 10, and that's Asus again, right? Let's show you the task manager. And in task manager, you'll see the 8 cores. These are 4 big, 4 little. It's Qualcomm Snapdragon 835, right? Let's launch Edge. Everything I'm doing is real, right? Like I've not pre-baked anything. There's no caching here. Everything is, I'm just launching for the first time. Instant smooth performance, right? So now I'm going to show you Pen quickly just to prove that this is just a PC. Everything I'm showing here is just a PC. All right, so let's show you Pen, right? Instant Pen smooth performance. Let's launch the Inkspace, for example, right? Look at that. There's no lag. This is all natively running as ARM64.
What about Bash?
Indeed. What about Bash? Well, it's just a PC, so you should expect Bash to be there, right? So let's try. Will that work? There you have it, Bash. Windows 10 on ARM, running Bash, Windows subsystem. So let me show you what I did. There's Ubuntu. We are launching Ubuntu Windows 10 on ARM here for the very first time. So this is a store app. So we've been working with Canonical over the last couple of weeks. This is a store app, and they're in the process of submitting this to the store. So anybody with Windows 10 on ARM can actually download Bash from the store and use it. So just to prove this is real, let me type something here. So I'm typing something called Screen Fetch. This is just a tool that shows you that this is real. As you can see, it's Ubuntu Bionic Arch ARM64, right? Linux. It seems to have an interesting bug where it's showing the CPU processor as 1.9 gigahertz when it's really not. The 1.9 gigahertz is small little core. As I said, one is clock frequent differently. So that's the demo. As you saw, this was a native experience running everything as ARM64. So let's go back to the slide. So apps, let's talk about apps. After all, people use Windows not for Windows. People use Windows for apps, right? Your apps are the key reason people use Windows so that their life is better. So let's talk about some of the app experiences right now. So if you think about apps, roughly, these are the big buckets of apps that exist on Windows. You have a UWP app. You have a desktop a Bridge Centennial app. You have a Win32 desktop x86 app. And you have a 64-bit x86 Win32 desktop app. And then you have an app with a driver. So these are things like your Symantec or your CD burning software or one of those things. And so when we first released Windows 10 on ARM in December with RS3, this was the situation, right? If you're a UWP app, you recompile to ARM, and you run natively. This is the golden path. It's simple, runs great, awesome. But if you're a Centennial app or an x86 desktop app, you run under emulation. And if you're a 64-bit app or a driver, we can't emulate them, and there is no support for those apps. So we got a lot of feedback around this, right? And it was a very planned decision. We knew that this is how we are going to do it. And so today, I want to announce that with the Visual Studio 15.8 preview, we have the ARM64 SDK support, right? What this means is it allows you to recompile all of your apps, desktop or store, to ARM64. The store will soon open up and accept ARM64 packages as well, right? So with this change, what's happening is the ARM64 is now a first-class citizen. It is on par in terms of tools and compiler support, just like an x86 or x64, right? It's just a PC. There is absolutely no difference, right? And so this was the picture we had when we first released a few months ago. And with today's release of ARM64 SDK, this changes to the following, right? Look at the performance column. Everything is best, right? Everything is running natively. There is no emulation in the picture, right? So if you're an ARM32, or if you're an ARM64 app, or if you're a UWP app, you can run as ARM32, or you can run as ARM64. The choice is completely yours, right? You have to decide whether you want the extra memory of a 64-bit process, right? You want more memory, then you can move to ARM64. If you don't have the memory requirements, you can stay as ARM32. Now, an interesting tidbit here, the ARM64 code generation is slightly better, slightly more performant than the ARM32, because the ARM64 instruction set has more registers. The code quality, the instruction itself supports more operations. So the code gen quality, the code quality is better. So if you have a CPU-bound app, for example, you may want to target ARM64. But for the rest of the scenarios, right, if you're a desktop Centennial, if you're a Win32 app, if you're a driver, the choice is simple. Just go to ARM64. Don't think, right? You don't even have a choice. Just recompile to ARM64, and you're set.
Can you install third-party ARM drivers on this?
Yes. It's just a PC. Yes. There is no signing. I mean, you got to sign with the WCL certification and the standard process as an x64 machine. But you can build your driver for ARM64. Right? So while this sounds real, how does that work in let me show you a demo. So we've had multiple reviews of the Windows 10 on ARM devices, and a lot of the reviewers actually, the battery life, LT connectivity, a lot of the usage resonated with them. But a lot of them also pointed out, oh, I need this one app. Oh, I need this one app. For example, last month, there was a review by CNBC, and the reviewer was like, I love the battery life. I love LTE. But man, I need OpenVPN. And without OpenVPN, I cannot access my, my enterprise resources. And so we were like, OK, let's take a look at OpenVPN. And we tried to recompile it to ARM64, right? And so as the name implies, OpenVPN, it's fully free open source. The source is entirely on GitHub, right? And so we downloaded the source, and we rebuilt it for ARM64. So any guesses how much code we had to change to compile the driver to ARM64? 5 lines, 10 lines, 20? 1 line? 0, 0. We had to change no lines of code. And I'm going to show you quickly a demo of exactly that. So let me switch over to the demo machine. So what you see here is Visual Studio. Now, OpenVPN uses a bunch of source file, make file, console building steps, and not Visual Studio solution files. So what I did is I actually created a driver solution. I opened Visual Studio, file, new project, created the WDK driver. I don't know if you guys in the room are familiar with that, but it's standard process, nothing special here. In the drop-down, as you can see at the top, is ARM64. I chose from the drop-down ARM64, and that's pretty much it, right? I added all the solutions, and I'm building it for ARM64. Now, as I mentioned, OpenVPN uses a bunch of config files and make files, and so they define a bunch of headers and constants, which on their console, and I had to update the Visual Studio project files to add that. And that's pretty much the extent of my changes. That's all I did. This is it. These are the things I added here. This is because, as I said, they have a console kind of building step, and that's pretty much it. And the only thing I had to change here was actually the version number. NDIS, the driver version number for ARM, was revved from 6.1 to 6.3, and so I changed it to 6.3 here. That's pretty much it. So let's rebuild this just to prove that this is real. So let me make a change here just so that it feels like there's some code here. And let's rebuild it. As you can see, it's building real time. That's it. It's built. So if you open up Explorer, you will see we have the ARM64 driver. That's it. It was as simple. We changed 0 lines of code. Nothing like, it's just, as long as you have standard Win32 APIs, there's really a whole lot to do, right? So let's switch back to our presentation. So you might be thinking, that sounds like a really simple app. Sorry, before I go back there, the other thing to keep in mind is we actually reached out to the OpenVPN developers, and we told them that, hey, we already recompiled your app to ARM64. Would you be interested in taking back our changes? And so they were very open to it, and so we're submitting PR back to them, and hopefully we can release this publicly pretty soon once they accept our changes. And so it's already in that process there. So you might be thinking, the OpenVPN driver, it looks simple. I just saw like 5 C files. I saw like 5 header files. That sounds like really simple. What about a more complicated app? So we reached out to VLC. VLC, I don't know if you know, is one of the most commonly used software on Windows. It's a media player, right? It's open source, and it's extremely popular. We know that based on our usage, right? So we reached out to VLC, and we were like, hey, are you interested in porting your app, your desktop app, to ARM64? And so John Baptiste, who's the main developer for VLC, he was like, yes, we're in, we're keen, let's try this out. And so we shipped him a couple of devices, right? We loaded them up with Windows. We gave them preview tools. And in shockingly short order of time, they had this up and running. In fact, we have folks from VLC in the room. I don't know if Hugo's here. Maybe, oh, there he is. There's Hugo. So he's from VLC. So if you do actually have questions on what they did, you should reach out to him. Again, just to belabor the point, when I asked John Baptiste, like, how much code did he have to change? His answer, 0. He changed 0 lines of code. His biggest problem was, again, VLC has its own homebrew way of building things. And so ingesting the latest Visual Studio Preview compiler into his build system, that was his biggest challenge. Changing code, 0. He didn't have to change a single line of code. Everything just worked. So let's see this thing in action. I have the native VLC actually on my machine right here. So this is it. This is the ARM64 VLC that I'm launching right? So let's play a 4K video just to prove. That's Xbox. That's an Xbox video, right? It's full 4K. No glitching. Extremely smooth, right? Like it's just like native. It is native. So let me jump in between just to show you, right, the performance. Look at that, no lag. I can skip anywhere I want. That's 4K video. Sweet. So now the paranoid in the audience, right? Just to prove that this is not some fake thing, let me launch Task Manager, right? I'm going to show you that it's a 64-bit app. If you go to VLC, you can see that it's a 64-bit app, right? So this is not some hand magic here. This is the real deal, right? And then for the really, really paranoid, let me launch another tool. I'm going to show you the headers of VLC, and you can see that it's actually ARM64. All right, so when an executable is recompiled, you actually can see the headers, and inside the headers tell you what architecture it is. And so if you look at, so I'm using some pretty old tool here. You can see the value here. Let me zoom in, right? So AA64, that stands for ARM64. The meaning unknown there really means that this tool has no idea about ARM64. That's why it's like he doesn't know what this value means. That's why he's writing unknown, because they've never seen ARM64 in their life. Not surprising. So let's go back to our presentation. Right? So as you saw, it was not that hard to recompile your app to ARM64. We showed you a driver. I showed you a really complicated app in this case, right? 0 code changes. It's not that hard. It's just Windows. So let's recap the effort required. So if you're a neutral app, for example, PWA, Twitter is a great example. You don't need to do anything, right? It runs natively. It uses the power of Edge, right? It's always native. It's JavaScript. You don't need to change anything. Your package is neutral. It just runs natively on this. Great. If you're UWP, based on our experience, you don't have to. It's typically 0, right? Let me give you a good example. Yesterday at our booth, there was a developer at Build. He came and he wanted to try out his app, and he only had an x86 version. And so he installed the app on the Asus device, and he felt that the performance is not great. I see a little bit lag. Today morning, he comes back. He gives us a USB, and he's like, hey, I ported my app to ARM. Can you try it? And boom, it worked first thing. There was no change, nothing. All he did, he went back to his hotel, opened up Visual Studio, created an ARM package, gave it to us. 0 changes. It just worked, right? And we've seen this over and over again. Inside Microsoft, every one of our UWP apps, 0 changes. They just submitted ARM, and it just works. Like, you don't actually have a lot of effort. Now, if you're a desktop or a Centennial app, there is some work. As you saw, the sources file, right? We may have the build thing. We have some sort of work there. The key thing, though, to keep in mind is third-party libraries. If you have a Win32 app, you may have third-party libraries and headers. Now, these things we need to make sure are available in ARM version. And in fact, that's where we need your help, right? So we are reaching out to various third-party developers and asking them to recompile for ARM. This way, any app that relies on ARM64 has your libraries already, has your headers. And if you need test devices, please do reach out to us. We are more than happy to give you loaner devices if you're local. And then if you're a Metro app, Win8 Metro, there are quite a few of them in the store today, surprisingly. Please move to UWP app, right? Stop and go to UWP. This gives you all the benefit of UWPs. You can run on Xbox, and then you'll fall in one of the above buckets, right? That's it. So submit an ARM. So let me show you some telemetry from our store. 21% of the UWP apps today run as x86 on this device because they haven't submitted an ARM package. 3 to 4% are 64-bit only, which means they don't run on this device either at all, right? 64-bit, we don't support 64-bit. So given the simplicity, it's not a lot of effort for you to submit an ARM package. There is really no effort required. So please submit an ARM package so that you can get all of these apps running on Windows 10 on ARM. Another one of our quotes from one of our MVPs. He recompiled all of his app. It has 8.5 million lines of code. It just worked, right? No changes. So that's it. This is it. There's one checkbox. One checkbox. That's all you need. Make sure to submit a package with ARM. And then if you uncheck that checkbox, with the preview, we added a new bump in the road. It's a minor bump. If you uncheck, you'll see a prompt that says, hey, are you really sure? Are you really, really sure? So most people may or may not notice that, but that's a small bump we added. Now, you might be thinking, since I keep talking about ARM64, where is my ARM64 dropdown? Well, right now, ARM64 support is in preview mode, and that's why you don't see the ARM64 dropdown in there. As soon as it comes out of preview mode in the next, in the short term, you will actually see ARM64 right there. So with that, let me hand over to Arun, who runs our software engineering team, and he will talk to you in depth about how some of these things work. Thanks, Hari.
So far, you've heard about what it would take to move an app to native ARM64. But what about all those apps where the developer might not be around anymore, or they simply just haven't had a chance to port to ARM64 yet? Well, for that, we have in the Windows on ARM OS an x86 emulation layer. So what does this do? This is basically a dynamic binary translator or just-in-time compiler that's able to translate blocks of x86 machine code to ARM64 code on the fly. And it does this in a manner that's completely transparent to both developers and users. So it's able to run apps completely unmodified. Now, generally getting this to perform well is a difficult proposition. So we've done a lot of engineering investment to make this run well. We've done a lot of optimizations in the just-in-time compiler. We've done some work around persisting and optimizing blocks of code that were previously translated and persisting those for future use. And we've also developed a technology called compiled hybrid portable executables, which I'll talk about in a little bit, which also help accelerate the performance. So here's a quick system architecture diagram on what this looks like. Here you see a native application. So Hari talked about this earlier. So for example, Edge, Cortana, Shell, these are native ARM64 applications. So typically in a native process, you'll have executable, which you see at the top. Then you have a bunch of system DLLs that they depend on. So system libraries, those are native. And then you have a special system DLL we call NTDLL, which is how applications on Windows talk to the operating system. Underneath, in kernel mode, so that's all user mode. In kernel mode, you have the Windows kernel and the drivers. Those are also all native ARM64. And then those interface with the processor, the GPU, networking, et cetera, all the physical hardware peripherals. Now, an emulated process kind of has two halves. It has a part that's depicted here in orange. This is the x86 binary, so something like Photoshop. And then you'll see there are also the system DLLs, the x86 versions loaded in the application. And then underneath that, we have something called WOW, or the Windows on Window layer. This serves kind of two purposes. First, it allows the app to talk to the kernel and operating system. And the second part is a CPU emulator. This architecture is the same architecture that we have on x64, 64-bit Windows on the x64 side. Except the big difference being that the CPU emulation is provided by the hardware. It's able to directly execute x86 with hardware acceleration. On the ARM side, we don't have that, and that's where our binary translator plugs into that box and does extra work to translate blocks of code at a time and save those in memory or persist them on disk for future use. Now, if you look at this diagram, you may be wondering, why are we running all these x86 system DLLs when we have the native code? Why can't we just link the app directly to the native system libraries? Well, there's a little bit of background around that. If you think about how the x86 app talks to the binaries, the system DLLs, it has two things it does. It uses x86 calling conventions, which are different than the ARM calling conventions. And it also uses 32-bit data types, whereas the native binaries will use 64-bit data types. So you'll have to marshal the data types back and forth. Now, the calling conventions can be automated. You can generate automatic thunks that do that marshaling. But for the data types, it's variable. It depends on the signature of the API or how complex the data structures are. So developer engagement internally to the Windows team would be needed to write those marshaling layers for each API. And that's thousands and thousands of APIs. So a decision was made for engineering efficiency reasons to do all that marshaling at the system call layer, this bottom box here, which is only in the hundreds of APIs in size. And that's the job of the Windows on Windows layer, the WOW layer, to do that marshaling. All the rest of the DLLs just run on modified x86 code. Now, that's a great design simplification when the emulation can run in hardware. But when it can't, it's kind of inefficient. So one of the things we've built with the developer division is a technology called the Compiled Hybrid Portable Executables, or CHIPY DLLs. And what these things do are they basically make the right trade-off that we discussed before, where they automate the calling conventions, so you basically can marshal over to native ARM64 calling convention, but they still run ARM64 native code against 32-bit data types. So the data types all stay marshaled at the bottom. So effectively, you can think of these as perfectly pre-compiled to run in an emulated process. And they give us like basically hardware native speeds for the system binaries. So now if you look at this process, you'll see you have a portion of the code that's orange, that's the emulated code. You have the system binaries in WOW, that's native. And then you have the kernel and drivers, which are native. And so the performance you get is going to be based on how much the code is split between each of these categories. So if you look at it on a scenario basis, if your app is a CPU-intensive app, so most of the code is going to be in the orange box or the chippy DLLs, you're going to get good performance. If you're an I/O-intensive application where most of the time of the application is going to be spent in the kernel or talking to devices, you're going to get awesome performance. If you're a GPU-intensive application where, again, most of your cycles are going to be spent talking to the graphics hardware and not in the emulated portions, you're also going to have awesome performance. So this all sounds great, but you're probably wondering, how well does this really work in practice? Well, I have a demo, a couple demos I want to show you. So go ahead. So here I have a game. It's Asphalt 8. It's been paused previously. I'm going to go ahead and resume it. And you can see here, this is an x86 app. It's fully emulated. And you can see it's actually really smooth, ultra smooth, great frame rate. And so this is showcasing all the optimizations we've done in both the just-in-time compiler, but also the ability of these emulated apps to get directly at the raw GPU power. Pretty good. Well, maybe not my driving, but let me go back here. I also want to show you another application. And this one is Office. So Office on these devices is actually emulated, but it's been optimized for ARM using the chippy technology that I just spoke about. So here I'm going to fire up a Word document. This is like a heavyweight Word document that has a bunch of pictures in it. So it's firing up. And so here you go. I see a bunch of pictures in here. Everything's smooth. Feels just like a native app. I can even get a pen here. Go into the tab, select highlight. Oops, get a highlighter. You can see it just works. Ultra fluid, just like with a native application. So this is a chippy Microsoft Word. Don't save that. I also have a loan amortization schedule. Let me launch that. So this is a large Excel spreadsheet, again, showing you what we can do with chippy technology. I'm just going to zoom out here, select these two columns, principal and interest. There we go. Let me go ahead and maybe get a 2D, maybe 2D stack chart. There you go. Really fast. Let me change the loan amount maybe to 50,000. Whole thing updates in real time. You get an even good loan rate, maybe 1%. Everything updates in real time. So really fast, smooth, ultra efficient. So this kind of really showcases the best of the emulator and the chippy technology. And the best part is, since this is actually technically still an x86 application, it's 100% compatible with the whole ecosystem of x86 Office plugins. So it's kind of like the best of both worlds. So with that, I'm going to hand it back to Hari. Thanks.
So for the folks who are not sure that this is x86, you can actually see it in Task Manager. Right? Let me launch it again. Oh, actually, you have Asphalt there anyway, so you can see it. Look at the details. And if you look at the details, you can actually tell, you can find out if it's, it's fine. It's too much work right now. So don't worry about it. It is x86. So let me switch over back to our presentation.
Game ran well.
So let's recap. Right? So what we talked about till now, we showed you how to make Windows 10 on ARM run well on Qualcomm Snapdragon processor. We talked to you how we have tools now so that ARM64 is a first-class citizen. And then we talked about the x86 emulation layer. This is done for the day zero problem, right? Now that we have given you tools, it's not I don't think it's a reasonable expectation that most people will recompile. Nobody's going to run out today and be like, oh, let me recompile all my apps, right? That's just not reasonable. And so that's why we did x86 emulation layer, so that at least on day zero, all of the apps that you care about, at least they work. And then this is still a journey. It's going to take you some time. It's going to take us some time, right? And to create ecosystem change here. Now that we have the tools out there and the devices out there, more and more people will start using these devices. There's going to be pressure. There's going to be some pressure from the customers on the developer saying, hey, I want to run this more on my device. Please recompile, right? So it's a cycle. It's going to take time. We're still very much in the beginning of our journey, right? And this is how it's always been. If you think about many, many, many years ago when Intel first came out with x64, right? We had the WoW layer so that x86 apps just run. and then we release Visual Studio so that you can recompile all your drivers and your apps for x64. So that's how it plays out. Anytime Windows or any operating system, Apple for that matter, supports a new architecture, it takes time. On day 0, you have an emulation layer to support the existing class of apps. And then over time, new apps come in because the tools are there. The market pressure is there, the TAM increases. And so that's how it changes. And so we have only 5 minutes left, and this is the last slide. I just wanted to quickly go through some of the best practices for the developers in the room. What we've seen is that a lot of UWP apps make an assumption. Hey, if architecture equals ARM, then it must be a phone. No. So Windows 10 on ARM is here. It's a PC. It's desktop. If you want to detect if it's desktop, use the device family API. Do not rely on architecture. That is the wrong check. In fact, a lot of apps, Paddington is a good example. A lot of apps assume since architecture equals ARM, they don't even show you your maximize, minimize button. They run it in portrait mode. So please don't do this. If you want to check whether the device is ARM, you can use isWow64 process 2. That tells you exactly what the architecture is. We've seen websites offer only 64-bit because they are not checking the client correctly. So if you're trying to check for ARM for x64 machine, please look for the x64 string in user agent. Finally, if you're an emulated app and you really are interested, hey, how do I make sure my emulated app works well? I would say the first P0 is don't worry about it. Don't think about how the emulation works. Just assume that it works. Don't try to do anything special. But no, you still want to really, in that case, I would say, try to generate the fastest code you can. Use all of the compiler options. Decide between OS and like size and speed. Make sure you use SSE2 instructions. And then finally, the one thing I would say is unaligned. We've actually seen some games use something called unaligned structures. And without going into a lot of details, don't do that. That just hurts performance on ARM. It hurts performance in general, but don't do that. That's just not a good idea. And with that, this is our final call to action, right? This is our main developer page. It goes live today. We have tutorials. We have short videos that tell you how to recompile your apps to ARM64, how to submit apps. So we have very simple walkthroughs there. And visit our booth if you really want to play. With that, I am done, and I will leave the room open for questions. I have Arun. I have other members of our team here also, so if you want to ask questions, please go ahead. Mary. Thank you. That's right. So to repeat the question is the WSL Linux that we are loading is an ARM64 Linux, or is it an x86? And the answer is it's an ARM64. I showed you in screen fetch, it was Ubuntu. It was Ubuntu built for ARM64. We are not running x86 Linux in there. Java will run under x86 emulation. And as I said, the SDK is available today. So if you have Java developers in the room, you're welcome to recompile. Use the Ubuntu Java. That's true. That's a good point. Yes. Sorry.
Was this Windows join domain?
Yes. It's just Windows. In fact, my machine that you saw is my work machine. It's domain join. It's full domain join and AAD join.
It's not a separate SKU. It's all the features that you like in Windows are on these devices.
Sorry, that goes. Go ahead. So the question is about Chippy, if it's available for third parties. Right now, the emulation is such an early project that we haven't opened up Chippy yet. Our answer to the people who want to recompile is please recompile to ARM64. That's really the long-term play. The long-term play is for us not to live in the emulation world, right? The long-term play is go to ARM64.
Yep. To specifically talk about that, the Chippy technology comes useful in really two kinds of scenarios. One is where you are an x86 application that needs to load in third-party ecosystem of plugins. And to retain compatibility with that, you still have to be an x86 app, and you can streamline portions of the code that you control. That's essentially the Office scenario. But in any other scenario, you're better off just porting the whole app directly to ARM. There's still some overheads with Chippy. It's not fully like a pure native software. Good.
Will you port Visual Studio to ARM?
If you go back to my original slide about the device categories, the devices here are designed for mobile, lightweight, consumptive styles. And if you're building devices for that audience, it doesn't seem like you should be using Visual Studio, right? Like if you want a dev box, there are plenty of other very good devices out there in the market.
But I think we will evaluate over time as usage patterns change, as hardware changes, what makes sense. So I wouldn't say it's out of the question.
Good.
When you compile for ARM64, how are we to treat ARM instruction extensions?
How are we to treat ARM? What do you mean?
Presumably on one architecture, we have one set of instruction extensions. On another chip,
No, so we target ARM v8 instruction set with ARM64, right? So if you're writing v8 instructions, all of the instructions in v8 would be supported.
so then we're to assume that all Neon or
Yes.
DSP or DFP extensions are running.
That's right.
And then in the future, if there's a new Neon V2, then we'll
That's right. So for things that would be differing between CPU generations, we would have the same model we have on other architectures where you can interrogate is processor feature available or whatnot.
It's just the same as Intel. On Intel, you query for SSE2, SSE4, AVX, MMX, right? You query for a bunch of CPU IDs, and then you understand the capabilities. And this is the same model.
Are those APIs in the
That's right, they are. Go ahead.
With the upcoming Qualcomm 845 and the ML support, are you looking into acceleration for WinML or is this future ARM system?
So there's two questions there. Question is about 845. So we are aware that this processor exists, but currently we're focused on the 835 today. Second question is on WinML and accelerating WinML. So WinML is built on DirectX, DirectX on DX12. So any processor that has it would benefit from that acceleration.
That's for the GPU part.
That's for the GPU.
For the 845, it has a special view.
Yes. Yes. So if you're talking about dedicated silicon support for other coprocessors, that's being evaluated across the board, and we don't have any update to share on that.
Go one.
for building apps, your app would be your ARM64. With third-party dependencies, what do you think is the better app?
So the question is, should I stay in x86 emulated mode, or should I go to ARM64, especially if I have third-party dependencies? My answer to it is always go to ARM64, and please reach out to the third-party developers whose libraries and headers you need, and ask them to recompile to ARM64. As I already showed you, it's not a lot of work, so just reach out and create the ecosystem motion here. Go ahead.
Where's the Surface ARM?
Right now, we're talking about these devices. Okay. Oh, sorry, go ahead.
Kind of in the same line. The only chipset supported right now is the Qualcomm 835. Is there plans to extend that in the future?
As of right now, we're focused primarily on the 835 with Qualcomm, but as time goes on, as the product space develops, I mean, we'll look at our options. But right now, we're 100% on 835 with Qualcomm.
Should we find like the OEMs to tell them to pressure on you guys to please have more devices and please get Microsoft to support them?
It's easier for us to do this if we can get apps ported to ARM64. So let's help us build the ecosystem out.
Sorry, at the back.
Yeah, so the question is, does the same WoW file system registry redirection come into play? Answer is yes. It's the same architecture for running x86 across the board.
The only caveat there is, this is going way into the weeds. I don't know if anybody cares, but Typically, the x86 apps, x86 process ask is wow process, right? And so they use those APIs. And so we always lie to those APIs and always tell them it's x86. And so if you try to query the native architecture, all of that is still telling you it's x86. Otherwise, the x86 app would think, hey, I'm trying to run on ARM, that makes no sense, and it would crash. So it's a little bit nuanced, but to your answer, the answer is yes. That's it. Thank you.